is that at low U, there is a Dirac semi-metal phase, and at large U, there is this nail antiferromagnet, which is an insulator. And then I hypothesized there was a direct second-order transition between them, and I derived a field theory for such a hypothetical transition. And the field theory, in the end, turns out to be something that particle physicists and lattice gauge theories have been interested in for different reasons. It's a field theory in 2+1 dimensions. It has some Dirac fermions with various numbers of components. It has a scalar field, and it has Yukawa coupling between them. And the leading summary of the property of the field theory is essentially these two equations. It's all very complicated, the analysis, but at the very end, what happens is all the couplings, in particular the nonlinear couplings, U goes to some fixed point of order epsilon, where epsilon is 3 minus d. So this is in d equals 4 minus epsilon space-time dimensions. So just think of these as universal couplings. Lambda is about a square root of epsilon. They're not quite universal. They are scheme dependent to a certain extent, but all of that cancels out when you compute a physically measurable quantity. So you can just think of them as universal. And the important physics describing this critical point is that there's only one relevant coupling, which is approximately S, the coefficient of phi squared. And this coupling T1 I can also use as my axis horizontally, so that the critical point is at T1 equals 0. And under the RG, this coupling flows away from T1 equals 0 in this very simple RG equations. And this coefficient here is traditionally called 1 over nu in condensed matter. So you could also say it's the scaling dimension of the relevant coupling. We call it 1 over nu, and nu is called the correlation length exponent. So if I've measured various correlation quantities, similar to what Krishna discussed, the correlation length xi would diverge as T1 to the minus nu, which is something you can figure out just by integration of this equation. I'll do that in a minute, in fact. All right, so the plan today is to now take this knowledge. This turns out to be a rather simple field theory for a quantum critical point in the end, and now go to finite temperature and look at issues having to do with transport. In particular, in this model, these are electrons here. This is the dispersion spectrum for electrons. These direct quasi-particles, just electrons. So they carry electronic charge, and I can just measure the conductivity. I know here I'll have a semi-metallic behavior. Here I'll have insulating behavior. And I'd like to know something about measurements in between. What would be roughly the properties in between? And I'll make sort of a leap that try to argue that we learned something, or there are some connections to transport properties of supersymmetric gauge theories that you can analyze using ADS-CFT. Now, of course, many of you will be very perturbed by this. The question they always get is, there's no gauge fields here, there's not even, and where's your large N expansion? How come you don't have SUN gauge fields with NC going to infinity and so on before you can even think of applying ADS-CFT? Fair enough, but I should say, especially when you talk about conformal fixed points, the issue of whether a fixed conformal field theory has a gauge field or not is kind of arbitrary. It's just a function of the formulation. This is one formulation of this critical point. It's strongly coupled. There could be other formulations which will contain gauge fields. And I'll show you an example of that today. And we'll also see more examples tomorrow. So really, for our purposes, it's just some strongly coupled conformal field theory in 2 dimensions, 2+1 dimensions. And what I will do is give a general discussion of transport properties of conformal field theories in 2+1 and also by comparison in 1+1, where much more is known. And that comparison will also give you some idea of what's profound and new about ADS-CFT. Yeah.
So in order for the gravity theory to be simple, so
yeah.
Really just analyzing classical gravity,
sure.
It has to be strongly coupled, the field theory?
Sure.
So what is the, when your couplings flow, the parameter you tune to have strong coupling is dimension, or what would you tune? How do you ensure that that's strongly coupled?
Well, epsilon is order 1, so by definition, everything is strongly coupled. That's really all I have to say. I mean, and you'll see the same for I'll talk about this particular gauge theory in the condensed matter language, and you have very similar phenomena there. As you just hold on a bit.
Yeah, I just mean.
Okay.
The coupling is just some number, like
Right.
it's epsilon, as opposed to having, in other contexts where you have duality, you actually have some coupling, you can tune it.
Yeah, well, unfortunately we don't. And, it's the 3 plus 1 dimensional, the 2 plus 1 dimensional case in many ways the most complicated because there is no such analog of the Etuf parameter. You're really always at, depending how you look at it, you're at Etuf parameter of order 1, which is strongly coupled.
That's strong enough to have.
Well, okay, let's hold on for those questions. Let me first just do condensed matter physics. So let me do straight condensed matter physics to figure out what are the transport properties. So what I want to do now is think about the phase diagram as a function of T1, and here's T1 equals 0, and I'm now going to add another axis, which is temperature. So here the ground states are shown over there, and now I'm going to put in temperature. So what happens here? Well, initially I told you that at 0 temperature you have this one relevant coupling. Now you have another relevant parameter. It's an infrared scale, so the geometry of your system now has the shape of a cylinder, and the circumference of the cylinder, this is the tau direction, and the radius, the circumference of the cylinder is 1 over temperature. And that's where temperature enters, but locally it's the same field theory everywhere. In this, it's a 2 plus 1 dimensional cylinder. I'm only drawing a 1 plus 1 dimensional cylinder here. Okay, so locally the RG flow is the same, but you have this other scale, which is just the inverse time. And so, but time has a very simple RG flow. Time is, time and space is just rescaled by factor 1 that defines the RG. So the RG flow of the temperature is basically dt dl normally we say this is z, the dynamic exponent, but here we have z equals 1. So that's the RG flow. It's extremely simple. You have 2 relevant couplings, and both of them run off to infinity. So here's my fixed point, and now things are running off to infinity no matter where I start. Okay. So now the only question I can ask is which coupling reaches infinity first? And that's going to demark different regions of the phase diagram. There's going to be some region of the phase diagram where T reaches infinity first, and that's obviously the case on this vertical line. If I was on this vertical line at T1 equals 0, then T1 won't flow, and T will keep flowing and run off to infinity, and I'll be in some infinite temperature limit of my field theory. Similarly, along this line, T will not flow. T is 0. And T1 will run off to either plus infinity or minus infinity. So T1 can have either sign. That's why we have 2 phases. And that's what's going to happen along this line and that line. So now the question is, if I start at a generic point here, how am I going to flow? Well, that's really very easy to figure out from here. So you can integrate these flows. So let's start with some T1. So T1 of L is e to the 1 over nu L times T1 of 0. But I'll leave the 0. If there's no argument, that's the bare value. And similarly, T of L is e to the ZL times temperature. And so now I ask for a length scale L. So when this becomes infinity, well, really, we don't want it to go to infinity. Let's say it goes to 1. Once T1 is of order 1, then I'm really well away from the critical point in a certain direction. So when is T1 of L equal to 1? So T1 of L equals 1, and I'll call that, let me call that L star. That's the usual L star 1 is 1. And then I get an equation for T1 of L star. So I get T1 times e to the 1 over nu L1 star is equal to 1, and this defines L1 star. And similarly, there's a RG flow of T. When this equals 1 in appropriate units, then you get the temperature times e to the z. Okay, I will just call that L star without a subscript. That's equal to 1. So now it's a question of which one of these is smaller. So there's some regime of the phase diagram where L1 star is smaller than L star. So then I reach 1 and I stop the RG flow. On the other hand, if L star is smaller than L1 star, then I reach 1 and stop the RG flow. So you can sort of guess there's going to be a region here where L1 star is smaller than L star. There'll be a region here where L1 star is, of course, this is all mod of T1. So they'll all do everything is symmetric for T1, L star. And there'll be a region in between where L star is smaller than L1 star. And what's the boundary between them? Well, the boundary between them is when these two are equal. So when L equals L star, this implies what? Well, okay. So it basically means T1 to the power of nu is, I hope I've got this right, is temperature to the power of 1 over z. Or the way you would write it is that right? So I take the power of this to the nu, 1 over z, everything's right so far. So that tells me that T1 goes as temperature to the power of 1 over z nu. So that gives me a crossover phase boundary. In between, that's the important crossover here from this very simple RG flow, where I have three different regimes, and this is really a very generic phenomenon near any conformal fixed point at finite temperature. I haven't made any further assumptions. This is just where telling you whether temperature is more important or the relevant perturbation from the fixed point. Now, lots of fancy things can happen in either of these phases, depending on what you're looking at. Over here, you could have Kost-Westphal transitions and Ising critical points and lots of other finite temperature physics that you'll find in your classical physicist textbook. But that's all contained in one of these two regions. And in between here is what we call the quantum critical region. So now let me draw another copy of this phase diagram, since you're going to see a lot more of it. So in terms of words, T1 and temperature, you got this phase boundary, general phase boundary here. And here you have what's called the QC region. And what is the important property of the QC region? Well, the important property, as we've seen, is that L star is smaller than N1 star. So the temperature has already become large. And the key thing here is the temperature has already become large while T1 is still small. So speaking colloquially, if you were sitting in the field theory, you've realized you're a non-zero temperature, but you haven't yet realized you're not at the critical point. So you may as well be at the critical point. So in this region, to understand the properties, you want the CFT, you want to work in the conformal fixed point at non-zero temperature. And that's really the zeroth order theory for that entire region. Of course, there are corrections depending on the ratio of L1 and L1 star, but that's the leading behavior. Conversely, on either of these regimes here, you're really not seeing the physics of the CFT. You'll end up seeing the physics of either of these phases. So here I can just write in, here I have the Dirac semi-metal. And here I'll have the nail insulator. Okay, so now at this point I can ask questions. Yeah.
Could you just say again what you said about why in the
Yeah.
middle region, why you feel the CFT? You said the word that last.
Oh, okay, so first of all, you accept that at this point, if I tune my coupling T1 to exactly 0, then clearly I'm at the CFT by definition at finite temperature. Now, if I move away, then those corrections will always be it'll involve a scaling function involves a ratio of this quantity to that quantity. So all corrections will be.
Yeah, no, I get it in the equations, but you said words about
Yeah.
having time to feel something.
Yeah. So.
I want to get the picture.
Okay, so the picture is that you're scaling out. You're at very short distances, at least in the field theory, you're conformal. So at everywhere in the phase diagram, if you're just dealing with the field theory, which there's a lattice to here, but forget the lattice. Everywhere in this field theory, at short distances, you're conformal. You're scaling out to large distances. Then at some point, you're going to realize, actually, I'm not at zero temperature. And that happens in this region here. Now, there's a much larger scale at which you realize, actually, I wasn't at the critical point. But at that point, who cares, since the temperature's already screwed you up. So in this region, in a sense, the conformality is broken first by temperature before anything else.
So first, as a function of
yes, correct.
The two infrared cutoffs, right? So you take
That's right. You just take the bigger one. That's all. Right.
Everything you said was static physics.
No, this is all for dynamics. This is for dynamical properties. This is for the quantum field theory. The temperature is a finite size correction only for the quantum field theory. So this is an intrinsically very quantum argument. It has a sort of a paradoxical implication that, in a sense, quantum fluctuations are more important at higher temperature than low temperature. Right? Yeah, but it's an entirely quantum argument.
But at some point, temperature gets larger than the ultraviolet cutoff.
Right. So I absolutely, thank you. So of course I said this is for ignoring the lattice, but if I put the lattice in, then there's something else happening at higher temperatures. Yeah.
Suppose I just sit at one non-zero temperature point that's somewhere in that region.
Yes. Yeah.
I'm happy to ignore the lattice.
Right.
And then I can ask questions about static properties.
Sure.
And do those static properties know about the quantum critical point down there?
Absolutely. Those static properties will be finite size correction of the quantum field theory on the cylinder.
And
So in that entire region, you have to you cannot.
The argument you made about as a function of RG scaling, you find out about the temperature before you find out about.
Well, let me rephrase it.
That could be a static argument.
No. Let me rephrase it. At short distances, you're in a quantum field theory, which is living in infinite space-time. You start rescaling to larger distances. At some point, you realize, I'm not in space-time, I'm on a cylinder. I'm not in infinite, I'm on a cylinder. That's what happens to you first in this region in here. That's an imaginary time, if you wish. So if I want to compute any physical observable, dynamic or static in this region, I have to account for quantum mechanics in a very fundamental way. Okay, now this took me many years to fully, yes.
Of course, you want to get to dynamical physics, I understand that. But
Yeah.
If I just limit myself to wanting to know about static quantities,
Yes.
do I need quantum mechanics?
Yes, you do.
Why do I need it for static quantities?
Well, because at least, if I want to compute it, say, in terms of, in fact, at T1 equals 0, where the same argument could be applied, everything is just a function of temperature and the velocity, and that's it. There's no other scale here. All your static properties will be just given by how quantum mechanics is cut off at the infrared scale of this cylinder. And it's just totally dominated by those finite. So it becomes a problem in finite size scaling. You can do it in multiple time, but it's entirely a problem in finite size scaling in a three-dimensional.
I go to length scales that are long compared to 1 over T.
Yes.
Then
Yes. Well, then eventually there's some classical hydrodynamics at long distance scales, but I haven't gotten there yet. Okay. But
you're doing statics or dynamics on
yes,
scales that are not long compared to 1
of order 1 over T. Right. So now the problem is, you're anticipating a little bit. At very long distances, you're going to go into some hydrodynamic behavior. But your transport, so that the equations then will be classical, but your coefficients, your transport coefficients, the values of diffusion constants, are fully quantum mechanical, but involve all this physics of the conformal field theory. So that's the purpose of this lecture, is to compute those effects. All right, but so there's a similar question that arises, say, over here. So let's go on this side, where, in a sense, things are more classical at low temperatures, which is when you first hear about it, it sounds crazy, but it is correct. So let's go down here. Well, at 0 temperature, I know I have a broken symmetry. So let me just say there's a broken symmetry here with phi not equal to 0. Now, at any non-zero temperature, what we call the Mermin-Wagner-Hohenberg theorem, or what somebody called the Coleman theorem, tells us immediately that you cannot have a broken continuous symmetry at any non-zero temperature. So in fact, this broken symmetry is restricted to be only at 0 temperature. And there is, if I was in some other dimension, or if this was an Ising order parameter rather than continuous, then there would be a phase transition here, which I won't draw in, which would be some Ising, classical Ising phase transition in that case. But now you can ask, well, what if I now want to look at low temperature properties here? Well, so there's a very large correlation length, which is diverging as t goes to 0. And on the scale of the correlation length, all of the physics is completely classical. So in fact, the long distance physics and the critical physics here will be described by an effective classical model, which would be a classical O3 nonlinear sigma model, and its associated dynamic universality classes. And so let me just say that this is what we call the renormalized classical region. Okay, let me write it up here. Renormalized classical, or RC for short is what many of us call it. And here the point is that in this region, the real distinction between this region here, there's a much cleaner separation of quantum and classical effects. Here, the quantum mechanics determines your ground state. And it's extremely important if you want to know the moment, the value of the moment, or the stiffness of various of the properties of the ground state. But if you now look at the fluctuations above the ground state, those are described by an effective classical theory. So quantum mechanics has short scales, and at very long enough scales, you become classical in a way. But here, things are a little more intertwined. You have to go to much longer scales where you get an effective hydrodynamic description. But there's an interesting crossover scale at temperatures of order at scales of order, energy scales of order temperature. We have equal mixing of quantum and classical effects. Yeah.
So the correlation length is that classical theory, as you said, it goes to infinity as t goes to 0.
Yeah.
What happens to it if you go upwards and get to that dashed line?
It still keeps going up, but at a slower rate. I'm sorry, depending which way you go. If you're coming down in temperature, let me come down this way rather than, okay. So the correlation is increasing here, and here the correlation length will increase as c to the well, you can figure this out from, it's basically going as 1 over e to the L star is the correlation length. So c will go as t to the minus 1 over z, if I remember right. Okay, so the correlation length is increasing here. You hit this crossover boundary, and now you're going to get a very different increase, which is controlled by the zero temperature classical field theory describing this thing. For this case, it will be an exponential increase, e to the 1 over t, and that's the e to the 1 over t of the 2D nonlinear sigma model, classical nonlinear sigma model. All right, that's a bit too complicated for this lecture. I'm happy to continue the discussion with Krishna later. I really just wanted to show here these, the very general argument establishing these phase boundaries, and the fact that in this entire region here, what you really should think about is the conformal field theory at finite temperature. Yes, those are the main things I want to get across. Yeah.
Okay, so let me just ask a more basic question.
Yeah.
So I'm not used to thinking about temperature being a coupling in the RG plots.
Okay.
So somehow it seems like what you're doing here is you're fixing the temperature in sort of lattice units, and then the RG scale of temperature, which you define down there, is you're somehow measuring the temperature in units of the...
Okay, well, so there is you take your theory and put it at a cutoff, and you say there is the cutoff defines some energy scale, right? And I'm fixing the temperature in terms of that, and do the RG. Yeah. And if I do the RG, the temperature becomes more and more important, because as I go to lower energies. Yes, exactly. Yeah, but it's no different from any other RG. There's different ways of defining the RG, but the most convenient ways I prefer to do it is to do the RG at zero temperature, and then supplement it with one exact equation. That's the complete description of There are other ways of you do the RG at finite temperature, and then it becomes a more complicated. Classical? No, this theory Z is one because of relativistic invariance, but you can certainly imagine other more complicated critical points, but Z could be a very highly non-trivial number. That's this Lipschitz scaling. Yes. Yeah. Yeah. What did I mean? Well, it means that the effective theory is two-dimensional, not three-dimensional. That's one way to think. That is, in other words, everything is constant in this direction. So the theory that causes loss of this long-range order at non-zero temperature, in that theory, I can assume phi is independent of time. That's one. Oh, I'm coming to that. Okay. So now the remaining part of today's lecture is to talk about this region here.
I had a question about
Yes.
insulating phase.
Yeah.
So when you say that the ground state is determined, when you say that the fluctuations are determined by an effective field theory, which is classical,
Yes.
you basically mean the correlation function of the order parameter?
Yes. Correct.
And that only at t equals to 0 is where that's relevant to this.
Right. So, it is true that for any theory, if you go to long enough scales, then the time component has shrunk to 0. If you go far enough out this way, this is shrunk to 0. So at some level, of course, yes, everything is classical. Okay, but is that a useful approximation? And I'm saying that that's a very useful approximation here, and it's really totally useless over here. If you want to get some numbers, that's not a very relevant regime to be working in.
Classical description is valid throughout that
Well,
insulating phase?
Okay, so let's see how to put it. These are all excellent questions. So for static correlation function at long enough scales, the classical description is always valid. There is some effective classical field theory. It may be a rather complicated field theory to describe, but true. The second question is, what about the dynamics? So now the dynamics, the question you have to ask, again, is what is the characteristic relaxation time of excitations? So the question then is, at the characteristic relaxation time of excitations, is the dynamic classical or quantum? And the answer is that at that time, here the dynamics is classical, here it's not. Okay, that's the most precise statement. It took me years to get that right. Yeah. No, I think they're really just crossover between two relevant operators. And there certainly can be phase transitions in here, but I think it's more correct to think of those phase transitions as properties of the T1 goes to infinity fixed point, rather than the T1 equals 0 fixed point. That's I think, the cleaner way to think about any possible phase transition here. Luckily, this model doesn't have any, so I won't address those issues. Yeah. So certainly, suppose the spin was two component, rather than being three component here. Suppose phi here, the vector phi was two component. Then you would have a KT transition in here. But that KT transition and everything about it, you just take a classical XY model to discuss it. Okay, and so it's really, the KT transition here is a property of the fact that at 0 temperature you have long-range XY order. So you may as well put T1 equals infinity in a sense. Go to the classical XY model, which has got XY long-range order at 0 temperature, trivially, and then look at its thermal fluctuation. That's the correct 0th order starting point to describe the KT transition. But that transition, that starting point doesn't work here. In this region, the correct 0th order starting point, you start with the conformal field theory. Great. All right, so as you can see, this quantum to classical crossover can be rather rich and surprising, but it's starting to be well understood in many models. All right, so now let's just focus on this regime. And we're just going to work with this field theory and actually try to do some computations. And so I'm just going to use the epsilon expansion. I won't actually do a calculation to order epsilon, where I'll wave my hands a lot. But I'll do at least one loop, a 0th order calculation. So we want to compute the conductivity. So let me define the current. So this electrical current is basically psi bar gamma mu psi. There are some flavor matrices here. I'll just ignore it. They don't play any role. So there's some conserved U1 charge here. One of the conserved there are number of conserved charges. One have to do with spin rotation. Some have to do with charge. And in fact, that is pretty much the conserved electrical charge. So that's my current. And I want to look at the J mu correlation function. So K mu nu will be J mu. Okay. And to begin, I'll just do the calculation in Euclidean space-time. And at the very end, as Son explained, we do an analytic continuation of Matsubara frequencies to get the retarded Green's functions, and therefore the conductivity. So the conductivity is going to be, well, one way to think about it is the Kubo formula, which I will use. Will be the sigma of Q and omega, let me say K and omega, will be, if I remember the signs right, minus I omega over K squared of the J0 retarded correlation function. And there's a, sorry about this. I got a sigma is normally defined as zero momentum, so let me just put a zero momentum anyway. I'll be showing you some plots of this. So. And it's the more familiar argument up to signs, which you may also be familiar with, is 1 over I omega of the longitudinal part of Ji, the spatial components, retarded. And these are equal by the conservation law, and I just leave that for you to figure out. Okay. But this is the one I'm going to use. So let me go ahead and calculate this at the conformal fixed point. Let's take the Euclidean space and compute K mu nu. So in this theory, well, the leading order is just a free Dirac theory. So you learn a huge amount by just doing the free Dirac theory. So let me just do that. So in the free Dirac theory, K mu nu is given by this correlation function. You got psi, you got a gamma mu here and a gamma nu there, and you've got the Dirac propagators. So after integrating over various momenta, it will be, let's see, lots and lots of indices, but it will be some basically gamma mu times p lambda, gamma lambda, p sigma, gamma sigma, p plus k sigma, gamma sigma, over p squared, p plus k squared, and I got to insert in here a gamma nu. There, and the trace over the whole thing. Okay, so these are the external vertices, the gamma mu and gamma nu here and here. There's a propagator here, so say this carries momentum p. This carries momentum p plus k, and you just get 1 over p slash. It's a very simple propagator, which I write as p mu, p lambda, gamma lambda over p squared. Okay, everyone sees that? Yes? Yeah. Okay, at the moment, right. So this, I'm working now in Euclidean spacetime. Eventually, I have to analytically continue, and this is a complex conductivity. It has a real and imaginary part, so there is no imaginary part. We just take the retarded correlation function. Okay, yeah, there's a DC conductivity, which will further have an omega goes to 0 limit, and okay, that is always real, without actually taking any real or imaginary parts. That follows some spectral rules. Okay. All right, so this is the loop diagram I have to compute, so I'll leave it as a homework. You just pull out your table of dimensional regularized integrals. I use the one at the back of Raman. It takes a few minutes and you get this answer. So what does this look like? And let me just do it in d space-time dimensions in general. What does this look like? Well, the first thing you could have kind of guessed, you're going to get delta mu nu minus k nu over k squared. That's got to be the tensor structure. And that follows from the fact that this is a conserved current. D mu J mu equals 0. There's a global symmetry. And so this has to be transverse, and so that's got to come out. And then what else? Well, there's no scale here. The only scale-dependent parameter you have the momentum itself. So what's the dimension of this whole thing? Well, there's d dimensions of momentum here, and then there's how many, well, these two cancel with this. There's basically 2 in the denominator. So you know this has to be k to the d minus 2. And then there'll be some constant, which I'll just call k sub d, which will depend on gamma functions and lovely things like that. So I'm sure you can all do this. Okay, so that's the result for the conductivity, which we now want to make use of. I'm sorry for a big confusion of notation. Let me call this Q. Right. So I'm going to use omega and Q when I'm talking about, spatial and temporal components separately, and I'm going to use P and K when I'm talking about space-time momenta. Yes. All right, so what is this equal to? So now I want to take all these steps. So that what I want to get is a retarded correlation function, the density correlation function. So let's look at this after doing analytic continuation and in real time. Here it's relatively easy to do. So I want the say J0 retarded. Well, that's going to be equal to K sub D times, so K is square root of, let me write it out, it's Q squared minus omega squared to the power of D minus 2 over 2. That's this thing here. Delta 0, 0 is, of course, 1. And what's K mu? So that's going to be the omegas. So the omega squared, and this may be a minus sign here, I don't remember, but we'll figure it out in a minute. Q squared minus omega squared. Yes, so that becomes a plus sign because of some metric somewhere. All right. Omega goes to I omega. That's how it becomes a plus sign. I remember. When you do here the analytic equation is trivial. Just take omega, replace it by I omega. That's it. Okay, so now I can do this algebra, and this is equal. Sorry.
This is valid in d less than 2? Or?
This is valid for d less than 4. So it is right. So naively, if you do the power counting, it looks like there's divergences. But if you maintain gauge invariance, even on a lattice, you'll find that they all cancel out. So the quick way to do that is to dimensional regularization. It will naturally give you the right answer. So there's no problem. This is perfectly finite. This integral, if you do it correctly, even on the lattice, perfectly finite and equal to this in 2 or 3 dimensions. Okay. Right. Okay, so that's so we can simplify this just a little bit more. It's KD times Q squared minus omega squared times D minus 2 over 2 times, this becomes Q squared over Q squared minus omega squared. Now I can absorb this in here, and I should have done that at step 1. In fact, it's better to take it down, and I'm just going to guess the answer, depending on what I know it is. It's Q squared over Q squared minus omega squared, and it's D minus 2 over 2. Okay. No, D minus, it should be 1 for D equals 2. So, well, that's not right. It should be 1/2 for D equals 3. Okay, so what is that? That's 4 minus D over 2? Yes, thank you. Okay. All right, so that's the calculation in 1 loop. All right, so now what about higher loops? Well, it's relatively simple. So basically the only thing we have, everything here you see is just power counting. The only thing that matters here is this number K sub D. So when I go to next order, go to order U squared, lambda squared, U to the 10th, lambda to the 10th, I'm guaranteed to get this structure. The momentum dependence is completely fixed. And so the only thing that can change is KD. So this coefficient here is what we call a universal number. KD is just a pure number characterizing the CFT. And so KD will be, some number plus some other number times epsilon plus some other number times epsilon squared, and so on and so forth. So depending on how hard you want to work, you can get all those numbers. So it's just some number like a critical exponent, and a lattice Monte Carlo person could probably get this quite accurately. Yes?
I mean, so there you took the two velocities to be the same.
Yeah, so I discussed that yesterday. Yeah, so I've assumed that. Just that simplifies life.
Right, but I guess I'm asking, if they're not the same, can you still...
No, you can't. Of course not. Then there's another dimensionless parameter around. Yeah.
Will you go to Euclidean to Minkowski?
Yes, that's
Why
right.
don't you change the third binomial to
Well, I only want the 0, 0 component. And I use the metric sign. What did I use? Yeah, okay. Maybe I probably screwed up many signs, but this is correct. All right. Okay, so let me now go over here. So let's look at some of this. Okay, so one of this, the D equals 2 case of this, you actually already know. All you conformal field theory jocks have seen it before, but in a very different language. So in D equals 2, what this tells you is that J00, and you can similarly work out JII, is some number, k sub 2, over q squared times q squared minus omega squared. Okay, so you all know conformal field theories in 2 dimensions, and you know how do you have currents there? What do they do? Well, you say they do something like this: JL of z, JL of 0 in space-time goes as 1 over z squared, and there's a number here which you call k, which is the level number of the Kac-Moody algebra. Okay. And similarly for right. And basically, if you take the Fourier transform of this, you'll get this. And this number k2 is related to that. Okay. Yeah. So this j left here is something like j0 plus I, j1, and so on. And j right would be plus or minus. So this is not a surprise. This is the answer that you already know. And there in 2 dimensions for many 2D CFTs, you also know the value of k sub d exactly through various other methods, because you happen to know in fact, it's quantized to integers and so on. And of course, and with very similar things happening in 3 dimensions, but now this number, k sub d, is not something we can compute exactly. We have no idea if it's quantized or not. It's some complicated series expansion in epsilon, and who knows what's going on at epsilon equals 1. So that's the essence, one of the problems that we want to look at. Anyway. Okay, so now I can take this and compute the conductivity. Yes?
Yes, in this expansion of KD, the 0th order in epsilon,
Yeah.
would that be equal to the level number over there?
Yes. 0th order in epsilon. Well, so 0th order epsilon have free Dirac fermions. So whatever the level number k is for free Dirac fermions, it will be equal to that, right? You bosonize free Dirac fermions, figure out k, and it'll come out equal to that. This calculation will give you the same answer. Yeah.
I'm just surprised that you don't get, at a critical point, you get some anomalous dimension as well.
Well, this is a conserved quantity, that's why.
So, yeah.
Because of the conservation law, there are no anomalous dimensions. Yeah, I should have mentioned that. Thank you. So generally, when you do this epsilon expansion, you get logs in the series. Yes, thank you. I didn't say that. You get logs at higher orders. Here, you're guaranteed that all the logs will cancel. And that's a consequence of this conservation law.
Why can it be k to some non-trivial power times the transverse tangential?
Well, this is, so once they aren't any anomalous dimension, it has to be this power, just by power counting. If you don't have anomalous dimension, then engineering dimension should work. It can't be anything else. Yeah.
So you want to the level is ambiguous, right? Optimization. It's not.
well, when you in the Bose-Einstein, but for the fermion, a free Dirac fermion, it's very clear what it is, right?
So I was wondering, in what normalization KD is constant?
What? So okay. So there is some normalization of you have some external gauge field, and you normalize the gauge field in some conventional way, or there's some charge. So good point. So normally, if I'm doing this for electromagnetism, they'll turn out to be a factor of E squared in front, where E is the electron charge, because that's how you normalize your gauge field. So you could think of J mu, really the more precise way to think about it is you have some external gauge field, which you normalize in some accepted way, and you take this is some external gauge field. So that's how you normalize J mu, and once you normalize J mu that way, KD is completely fixed. So for electromagnetism, there'll be a factor of E squared, where E is the charge of the Dirac fermions. Thanks. Okay, so now let's forget about 2 for the moment, and I can't move this up. Let's talk about, I'll leave that up. Let's talk about what the conductivity is using the formula that I just erased. Or I can do it over here. Let's keep it up for a while. So I take this formula here and plug it into the conductivity, and I get a very simple answer. Sigma of omega modulo some sign. So you can see now right away the q squared will cancel out, and this will become I omega, because this becomes 1/2. And the omega would also cancel out. So in the end, sigma of omega is frequency independent and equal to this universal number. So in 2 plus 1 dimension, the conductivity at 0 temperature of the conformal field theory is again this level number of the analog of the Kac-Moody level number. And generally, related to Sung-Six questions, there is a conventional normalization, and which I've invented so far, and that will come in here. And in fact, if you put in factors of h bar 2, there's an h bar, which is the correct units of conductivity. So these are setting units right. And this is exactly the electron charge. There's no ambiguity about it. It is 1.6 10 to the minus 19 coulombs or whatever. That's the number you got to put in here. And E squared over H, that's the units we conventionally use. So since I've brought factors of 2, it's H bar if you do the calculation this way. E squared over H is the quantum unit of conductance, which is, the resistance is about 26 kilo ohms.
So this is 2 plus 1, right?
Yes. Okay. So this, now we have an important prediction that at this quantum critical point, then, the conductivity is a universal number. And I'm running out of time, but one of the messages I want to get across is that this will play a role quite analogous to 8 over S for the super Yang-Mills theory. It's a universal constant that characterizes the transport properties. Any other questions? Okay, well, if this was the end of the story, then I wouldn't need ADS CFT. I just have to do more and more epsilon expansion. But this is not the end of the story, and the reason it's not the end of the story is that, if I go back to this picture over there, this whole computation was done at 0 temperature. And I really should go to non-zero temperature to understand the real conductivity. So here you say, okay, no problem. Let me just do this calculation at non-zero temperature. Okay, so when you do that,
I just confused this
yeah.
simple calculation. You put the G00 correlation to that formula exactly. You take when Q goes to 0.
Yes.
Then the numerator Q cancels, and we have omega, and another denominator we have omega to the power.
Well, D is 3 now, so it's omega to the power 1/2. So you get an I omega also.
Okay, then omega completely cancels.
Yes. Okay. Yes, it does. So that's one. And why should we be worried? Well, I guess maybe I should do this argument now. Yeah, since I have the notes. So we learned from Sohn that when you go to finite temperature at long enough distances, the correlation should be hydrodynamics. And if I look at this correlation function, it doesn't look like hydrodynamics at all. So the question you want to ask is, what would hydrodynamic predict for the long distance and long time form of the charge density correlation function. So this was worked out by Einstein also in 1905 in a paper that said nothing about relativity, and I'm going to quickly review the argument here. What should hydrodynamic correlation, what did hydrodynamics teach us this should look like? Yeah.
Some kind of delta function here in these stories?
No, this is correct. There's no, at finite temperature you get a delta function. I'm coming to that. Well, one way to think about it in this picture, so what is this conductivity at zero temperature? You have all these states filled and these states empty, and you're coming in with an external AC field. So you have an AC field coming in, and that's creating particle-hole pairs. So all you're measuring is the cross-section of creating particle pairs. It's really not a conductivity in our physical way of thinking. For a conductivity, if you go to finite temperature, you have a very different picture. At finite temperature, you have some gas of particles and a gas of holes, which are not present at zero temperature by definition. You come in and you apply an electric field, and these particles and holes accelerate. And how they relax is what we want to figure out to get the real conductivity. This calculation has none of that physics. All right, so this physics of the relaxation of particles and holes, at least at long enough times, we can address by hydrodynamics. So let me review the hydrodynamics argument for the long distance charge density correlation function. So this is, Sohn has already done the more complicated case of momentum transport. This is baby stuff compared to that. So let me just do hydrodynamics. I have a very simple equation of motion, which is d rho dt. Now I'm going to use real time and not a relativistic notation. D rho dt plus del dot j equals 0. That's the equation of motion of hydrodynamics. And then the other equation is a constitutive relation, which is what is the current in terms of transport coefficients. So here, let's just think of in terms of Brownian motion and early 20th century physics. If you suppose you create a density variation, how is the current going to flow? So here's some as a function of x. Here's the density. And at every point, you have particles undergoing Brownian motion. Some moving this way, some moving that way, some moving here, moving there, and so on. And they're equally likely to be moving left or right. Now, so if I'm here, since there's a higher density on this side than that side, there's more particles moving to the right than to the left. So that tells me there's a net current, which is going to go downhill. Things I want to even out. That's just classical Aristotle physics. So this will be minus the coefficient we call the diffusion constant times the gradient of rho, and that's Fick's law. So this is just a phenomenological assumption on things wanting to maximize entropy and reach the optimum state where the density is uniform. But also imagine that these are charged particles as an external field, and that external field is also going to accelerate them with an electric field. So that's the expression for the current. Now I seem to have introduced two transport coefficients, the conductivity, which I want, and the diffusion constant, which I don't want. But they're related, of course, by the famous Einstein relation, which we can now derive quite easily. The way to think about it now is you imagine you had your Lagrangian, or your Hamiltonian, your Hamiltonian was h times some h prime minus mu times so this is, now think of rho as the charge density. So there's some number density here. I'm going to keep track of the charges. And then you add an electrostatic potential. So this is the charge Q, which I call E over there. Well, let me call it E then. But I'm going to leave it plus E rather than minus E. Imagine these are protons. What did I do? No. It'll be basically phi times rho, and rho is E times N. Okay. So this is the electrostatic potential that you're applying to create the electric field, and so the electric field is minus grad phi. Okay, this is just electrostatics. And so now what you can say from this is that you can, when the system finally equilibrates in the presence of an electrostatic potential, you can absorb the electrostatic potential into a space-dependent mu. So applying electrostatic potential is the same as changing your chemical potential by minus E times phi. So this tells me when delta mu is minus E phi, current shouldn't flow because everything is in local equilibrium. You have some local space-dependent chemical potential, and things have equilibrated in that space-dependent chemical potential. So if there is such a change in the chemical potential, the change in your density, dN, would be dN d mu times minus E phi. And so delta rho would be E squared phi, maybe, yeah. All right, I hope I get all the signs right, which were right in my notes. Looks like there's some sign wrong somewhere, but okay, I am to stop in 10 minutes, so forget about the signs. So now if I plug this in here, so we want J equals 0 when delta mu equals minus E phi. And this implies the famous Einstein relation that sigma is d E squared times dN d mu. Okay, so this is there's only one transport coefficient, which is relating the conductivity to the diffusion constant and the compressibility. Okay, so now I want to compute the density correlation function, and just as Son did, the way I'm going to do it is by applying some time-dependent chemical potential and computing the response in the density. That's the response function. So when I plug this in here, I get an equation. I combine these two, and I get an equation of motion, which I'll write down here. The equation of motion for the charge density is d rho dt plus d del squared rho. That's the diffusion equation. Whoops. D del squared rho is equal to d q squared dN d mu times del squared phi. So I apply some electrostatic potential, and this is the response in the charge density. Take the Fourier transform, just a couple of equations, and I get the final answer, which I will try to put up somewhere. Well, let's go back here. So hydrodynamics predicts that the J00 of R should equal to, let me see, it's E squared D times dN d mu over Q squared minus I omega plus dQ squared. And you compare this with conformal field theory at 0 temperature, and this is true in any dimension. You get G0, J0. This is now in D equals 3. You get is K sub D times Q squared over square root of Q squared minus omega squared. Okay. Sorry? Yes. So this is correct. So that's why this is hydrodynamics, which is only works at finite temperature at scales longer than the relaxation time. Yeah, so this is CFT at t equals 0. That's the calculation right there. Okay? All right, so clearly, when I go to finite temperature, something drastic has to happen. But I should say as an aside here, that if I looked at this in a CFT at t greater than 0 in d equals 3. So this is a calculation you can do, which I won't do. For any CFT in 2 dimensions, I can map the finite temperature problem to the 0 temperature problem by conformal mapping. I can map the cylinder to the plane. So if I know the correlation for 0 temperature, I know it at finite temperature. So here's the answer at 0 temperature for the CFT in d equals 2, which I wrote down. You do the calculation. Oops, I should say 2 here. What you find then is at all temperatures, J0, J0 is K2 times Q squared over Q squared minus omega squared. So this is in fact the correct answer. So this tells us that there's no hydro in D equals to CFD. So they're really, in a sense, much simpler. CFDs in 2 dimensions, in this case, will never equilibrate. They don't obey the laws of hydrodynamics. They don't diffuse. They're just, in a sense, free. And there's always some set of variables where they look like free particles. And so, but there are no collisions, and things are relatively simple. But CFDs in all higher dimensions are really much more complicated beasts. And that's really why, in a sense, there's never been any exact solution until this ADS-CFD approach, which in fact, I ran out of time, agrees with both of these. It agrees with this, and it agrees with this. And it's really the first calculation of any system where you can see this kind of crossover between these two limits. But you do not, this is never true for any CFD in 2 dimensions, in D equals 2. It's only in 3 and higher that things become much more complicated. Okay, I'm well short of where I thought I'd be, but anyway, yeah.
So, just for the fun of it, if we make D a non-trivial function of space-time.
D meaning which D? I have too many D's here.
The capital D.
There are 2 capital. One, this is the diffusion constant. I should call it something else. Let me call it D sub C. Yeah, D sub C. The charge diffusion constant. Yeah. What did you say about D sub C? Let me put this up here too. D sub C, D sub C. It's not space-time dimensions. Okay.
Yeah. Can you make the 2 results for some choices?
Well, no, obviously not. I mean, the frequency and momentum are entirely different. I mean, if you think of the physics, plot the imaginary part of these two. If you plot the imaginary part of this as a function of omega, this is the imaginary part of J0, J. This thing has a threshold at omega equals Q. It looks something like this. Okay. You plot the imaginary part of this thing here. It's some diffusive peak at omega equals 0. They're totally different. One describes relaxation and equilibration. The other describes singularities of a conformal field theory at some, because of some external frequency dependence. So it's like particle production. This is particle production. This is density relaxation. Yeah. I did. Okay. All right. Okay, fine. You're the boss. All right. So, yeah. So I made a number of physical points. So now one way to see now, so let's go ahead and try to repair this. So let's go to finite temperature and look at and do this calculation at finite temperature. Okay. So now I'm going to stick to 3 dimensions. In 2 dimensions, you can do it, but, well, nothing interesting is going to happen. We know the answer exactly. Just from conformal mapping, this is always true. So let's go to finite temperature, and you can, again, at this level, just do the calculation in Euclidean space, time, and then do the analytic continuation. But now the only difference will be that here, you're going to get sum on omega and integral over the spatial components of p, let me say dpi over 2 pi to the little d. Little d, I consistently use little d for space and capital D for space-time. So it's the same integral, but the only difference is I have a discrete summation over frequencies. Okay, so this is much more tedious now. You actually have to open a book on solid-state physics and learn how to do Matsubara frequency summations. I will let you work it out. Probably I don't want you to work it out. It's painful. Anyway, you can do the calculation, plug it in here, and what do you get? I'll just tell you what you get. So what you find is at sigma of omega then at finite temperature. So this is now D equals 3, T greater than 0, and at this point it's just a free field, free Dirac fermions. Seems like a simple enough calculation that somebody should have worked out at some point. But anyway, it wasn't. But here's the answer. So I actually don't remember the detail of the answer. But now you have a scale, and so things can depend on omega over t. And certainly when omega goes to infinity, you're going to get the same answer as you had at t equals 0, which is just kd. So this will just go to k3 over here. Sigma of omega. And here, I forget, you get some small frequency. I think it goes to 0, I don't remember. It's not terribly important. You get some sort of frequency dependence on the scale temperature. But most importantly, what you get now is a delta function here. And the delta function has, so the contribution is t. Well, there's an e squared that's been observed from it. It's basically t delta of omega plus various smooth terms. Okay, and this, what is this? Well, if you think about physically, it's obvious what this is. Here's the free Dirac fermions. You've created some thermally excited particles here. You have some thermally excited holes here. You apply an electric field. The particles move this way. The holes move this way. That's a state with zero momentum. But it's a state which carries current. And it's going to keep, these particles will accelerate forever. They're not colliding with anything, at least at this level. And since they accelerate, rather than move at a fixed velocity, in the linear response theory, that appears as a singularity at zero frequency. Okay. And so that's the physics of this. And the density of these particles above the ground state is proportional to temperature. As measured by the conductivity. The density itself is a different quantity. The proportionality on temperature you can deduce by dimensional arguments because the conductivity is dimensionless in units of E squared over H. And this is dimensions of inverse energy, so this has to be one energy. That's it.
So in the geotemperature, that kind of thing doesn't happen?
In the what, sorry?
In the geotemperature, you said.
No, this doesn't happen. This delta function is... The difference is just this fact that over here, if I did a summation over discrete frequencies rather than integral over frequency. Now, in Matsubara time, this is not such a serious... If you were working in Euclidean time, it's not such a serious thing. You would think, well, what's the difference is summation or integration? They're almost the same. That's how you do integrations anyway. But when you do the analytic continuation, the distant difference is dramatic. So this is all a consequence of analytic continuation. But physically, it's really very clear that this is what must happen. This is the real part of the conductivity, sorry. Yeah, so the imaginary part has an I omega. Right. Thank you. It should, okay. We know in the end it should look like, where did it go? This. But not yet. It doesn't. Well, that's the density correlation with the conductivity. Of course, they're related, but it doesn't yet. Well, so this is where now we've got to repair this damage, and you say, okay, no problem, let me just go to 1 higher order epsilon. Everything will be fine. In fact, things get worse. You get even more complicated singularities, and at every order, things get even worse. So at that point, you give up and you have to try to think physically. And you really have to sum multiple collisions of particles as they're moving through a medium, just as Sohn emphasized. And what does that for you is the Boltzmann equation. So you have to write down a Boltzmann equation, in this case a quantum Boltzmann equation for these particles. And this whole formulation in terms of quasi-particles and the Boltzmann approach intrinsically is very special to epsilon equals 0. For large epsilon, it's not at all clear this is even quantitatively reasonable. It's something really different happening here. But anyway, that didn't stop us from doing the Boltzmann equation. This was work I did with Kedar Damle, not for this field theory, but actually the scalar field theory in the mid-90s. And when you do the actual theory, what you get is the following sort of result, qualitatively, which you can also guess after the fact, is basically what you should get. You get a sigma of omega in the Boltzmann theory, which has what's called a Drude peak, here, and then it eventually goes to this value here. So this scale is of order temperature. This scale turns out to be of order epsilon squared temperature. And this scale turns out to be 1 over epsilon squared. And you can sort of guess that after the fact. If you think like Boltzmann, you'd say, well, all you need to figure out is some collision rate of these particles. So 1 over tau collision. Well, the collision rate got to go as u squared, and u is of order epsilon. Oops, sorry. Yeah, when you integrate out phi, you get 4 Fermi term, and anyway, it'll go as order epsilon squared, I'm pretty sure. Okay, maybe for this theory, there's lambda is square root of epsilon. Maybe there's something at order lambda squared. I'm a little bit confused. Or I'll get that straight. It's some power epsilon. Certainly for the scalar field theory, it's epsilon squared. So it's got to be, just to Fermi's golden rule. You have these two of these particles. They're going to collide and scatter, and compute that rate for weak interactions using Fermi's golden rule. That's really all we did, and put that into the Boltzmann collision term. And so this will give you some epsilon squared. This is a time, so it's the only time scale everywhere is just temperature, so it's got to be epsilon squared times temperature. And once you know that, then the conductivity, sigma goes as is proportional to the collision time, just like the viscosity. And so this will go as 1 over epsilon squared. That's basically the argument, and it's just verified by detailed calculation. So you get very strongly frequency-dependent conductivities. The actual conductivity here, this number here then, would be related to, since this is indeed obeyed, now if I apply Kubo formula to this rule, I will get Einstein's relation. This value does obey that relation. It's E squared d times dn d mu. And this works. So the Boltzmann equation does obey the principles of hydrodynamics. It's got this H theorem that ensures that entropy is maximized. And so as one of the consequences is that you will obey the Einstein relation, unlike the previous description. I really should, yes.
Why doesn't the lambda figure in the binding expression?
Lambda?
Lambda meaning
Yeah, so lambda is about epsilon. This is what I got a little confused about. This could be epsilon for this theory if it's lambda squared, but I think it's lambda the fourth, the collision rate. I don't remember actually. I'll get it straight by tomorrow. Modulo that. If I had just this theory and I was looking at spin transport, all of this is correct. So it's almost here I have two conserved laws at this critical point, both charge and spin, and I can say all of this for the spin diffusion, the charge diffusion, or the spin conductivity, the charge conductivity. All these things apply equally. All right, so I guess I ran out of time, but just 1 second. So what I will do next time then, contrary to my plan, is then just, okay, we did this in the mid-90s, and then when I heard about Sohn's and other people's work on ADS-CFT, I said, in our desperation, we said, well, who cares? Let's just solve this for super Yang mills anyway, see what you get. And I'll talk about that next time. Yeah. No. Good question. So excellent question. Well, how come I get a finite conductivity in a system that conserves momentum? That has to do with the fact that the chemical potential is 0 and there's particle-hole invariance. So remember here, notice I have by particle symmetry equal numbers of particles and holes. So when I apply an electric field, the particles go this way and the holes go this way. So yeah, but the important point let me make. So this state where the particles are moving this way and the holes are moving this way is a state that has finite current but 0 momentum. So it's possible to get a state, and in fact that's the maximum entropy state. There's a state which has 0 momentum and finite current. And so momentum conservation is not that important. You can still get a finite conductivity because eventually what will happen is that these will collide with each other, and they'll collide and relax to 0 current. So if I measure the current as a function of time, I apply an electric field, the particles accelerate, but eventually they'll decay to 0. And the conductivity, in a sense, is an integral over this. They will decay to 0, so you won't, and that's because everywhere, at every point, the total momentum is 0. That's an important point. Yeah, then there's always a delta function. Yeah, so that's a very serious issue. Actually, in many of these calculations, the ADS-CFT at finite chemical potential, they're simply ignoring that fact. Yeah, sorry. Yeah.
Is there any reason for the fact that if I look at the finite temperature one versus the zero temperature, the denominator in the finite temperature looks like 1 over the particle now relativity theory.
Yeah.
And the one for the zero temperature is 1 over relativity.
That's right. So there's a lot of things. So at zero temperature, you're really in a relativistic theory. At finite temperature, you're relativistic at small scales, but at long enough scales, you flow to the diffusion equation. So, I mean, this looks like Schrodinger's equation, but it, of course, differs in a very important respect that there's no I here. But, okay, yeah, other than that, it has the flavor of a non-relativistic. But it's dissipative. I mean, it's the fact that there's an I here. This is not the pole of a particle. This is actually a very broad peak because of this I. This has to do with, equation of motion of where the velocity is proportional to the force, not the acceleration proportional to the force. That's what diffusion is about. Okay, thanks.